So looking at page 322, we're going to take a look at 3 examples of these optimization type problems where we're trying to find the most of something or the least of something. And if you need to reference the kind of step-by-step guide on the previous page, you can. But maybe try a few of these without doing or referencing those so you can start to get the feel on how these operate. So the first one we're going to take a look at is kind of similar to the example that we did together in class, where we're going to build a box out of a piece of cardboard. They tell us that the box has dimensions, or the piece of cardboard rather, has dimensions of 25 centimeters by 40 centimeters. And in order to make a box out of a two-dimensional object, we're going to have to cut a square out of each corner and then bend up the sides to create the walls of this box. So if we drew a little picture, we'll say this is our cardboard, and then we are 25 centimeters this way, 40 this way, and we're going to have to cut out a square out of each corner, and maybe we'll label the sides of this square X. So in order for us to create this box, we're going to fold up the sides to make the wall, and we're trying to find the size of the square that will produce the container that will hold the most amount of soup. So it doesn't really necessarily use the words maximize or minimize. In this case, it's saying the most amount of soup. So most, we can kind of think about a maximum. So we're going to maximize something, and if we're going to put soup into this cardboard box container that's built in the end, that's most likely referencing volume, like the most amount of a liquid we can fit inside of a container. So we're going to try to maximize the volume that this box would create. So if we think of our primary equation, the volume of a, not necessarily a cube, but a three-dimensional object in this case, we are going to have length times width times height. Okay, so all those multiplied together. And if we were to visualize what the length, width, and height distances or values would be, let's see if we can kind of computate what those would be. So length, they said 40 centimeters long, so length is going this way. So we have 40 centimeters initially, but then we're cutting out a distance of X on either corner because of those squares. So our length would be 40 minus 2 X's. So we start with 40 and then cut away those 2. The width, very similarly, was 25, but we're going to cut away 2 corners. So we can do 25 minus 2x. And then the height of this box, if you think about it, would be if we fold up the sides, which is basically this distance left. So that would be x. So looking at our primary, we have two variables in there, which is fine. It's not like we have to think of a secondary equation to help us get rid of a variable. So from here, we're going to take our derivative. So dv over dx, or you can write v prime, whatever notation you're more comfortable with. I might, actually, before I take the derivative, I might want to clean this up a little bit, because I'm multiplying 3 terms together. So I'm going to kind of cut some corners here. If I were to go through a FOIL process with these 2 binomials and then multiply an x in, I'm going to have 1000x minus 130x squared plus 4x cubed. Okay, kind of movie magic there, just jumping straight to what the expansion would be. Alright, so now derivative, we'd have 1000 minus 260x plus 12x squared. If we think about factoring, because we want to set this equal to 0, maybe we can pull a 4 out of all those. So 4 out of 12 would be 3, 4 out of 260 would be 65, 4 out of 1000, 250. Now, I'm pretty sure we can factor this a little bit further. You might have to go through the 8 times c method, what adds to b. Using a calculator, you'd probably have to figure that out because we're going to be dealing with some high numbers here. But again, I'm going to kind of cut to the chase where we could factor 3x minus 50 times x minus 5. Okay, so it looks like our x solutions would be 50 over 3 or 5. Okay, these are kind of our critical points. Now, if we think about if we actually have to test both of these or none of these or just one of them, we're going to go back to our picture here. And notice how I can't make a cut more than half of 25, so more than half of 12.5, because there's no way I can cut more than half on each corner because I only have 25 centimeters to use. So since 50 over 3 is more than 12.5, we can kind of rule that one out. So it looks like our only critical point is 5. So if we go ahead and test it, let's see, my lowest cut could be nothing, so I'll go from 0 to 5, and my highest cut is 12.5. Okay, because I can't cut more than over halfway of 25. So kind of using our sign chart there, we can fill in those values. You really don't have to put in the lowest and the highest amount possible. Sometimes those are going to be a little bit more difficult to figure out. But in any case, you just want to pick a number less than 5 and a little bit more than 5. So you don't have to get too crazy with the values that you pick. So we'll plug it into our derivative. So something between 0 and 5, maybe I'll just use 4 in case I couldn't figure out what the lowest number would be. So if I plug in 4 to my derivative, this would be negative, this would be negative, multiplied together would be positive. Something bigger than 5, maybe 6. This would be negative, this would be positive, so multiplied together would be positive. So based on our sign chart, notice how we are confirming that there is a max, okay, at 5, okay, that maximum volume. So find the size of the corner of the square that would produce the most amount of soup. Kind of run out of room here, so I'll go towards the top. We'll say a 5 by 5 centimeter square, because the derivative changes positive to negative. Okay, we confirm that based off our sign chart.